NENOMATICA, where mathematics meets YouTube excellence. In this lesson, we will factor an expression using Euler's identity for the sum of cubes minus triple product. Our goal is to factor x cubed plus 8, y cubed plus 1 minus 6xy. Step 1. Recall Euler's identity. It says, a cubed plus b cubed plus c cubed minus 3, a bc equals left parenthesis, a plus b plus c, right parenthesis times, left parenthesis, a squared plus b squared plus c squared minus, ab minus, ac minus bc right parenthesis. Equivalently, it equals 1/2 times left parenthesis, a plus b plus c, right parenthesis times the sum of squared pairwise differences, left parenthesis, a minus b right parenthesis squared, plus left parenthesis b minus c, right parenthesis squared, plus left parenthesis, a minus c, right parenthesis squared. Step 2. Express our polynomial in Euler's form. Notice that x cubed plus 8 y cubed plus 1 is a sum of 3 cubes x cubed plus left parenthesis 2 y right parenthesis cubed plus 1 cubed, and the term minus 6x y equals minus 3 times x times 2y times 1. So we can identify a equals x, b equals 2y, and c equals 1. Step 3. Apply the identity, substituting a equals x, b equals 2y, and c equals 1 into Euler's identity gives left parenthesis x plus 2, y plus 1 right parenthesis times left parenthesis x squared plus left parenthesis 2, y right parenthesis squared plus 1 squared minus x times 2y minus x times 1 minus left parenthesis 2, y right parenthesis times 1 right parenthesis. Step 4. Simplify the quadratic factor. Compute each term. 2y squared is 4y squared. Minus x times 2y is minus 2xy. Minus x times 1 is minus x. Minus 2y times 1 is minus 2y. So the inside simplifies to x squared plus 4. Y squared plus 1 minus 2x, y minus x minus 2y. Quick verification idea. Euler's identity guarantees that when a plus b plus c equals 0, the second factor becomes a perfect square sum form. Here, we use the full identity directly. So expanding the product would return x cubed plus 8, y cubed plus 1 minus 6xy. Final answer. The factorization is left parenthesis x plus 2, y plus 1 right parenthesis times left parenthesis x squared plus 4, y squared plus 1 minus 2x, y minus x minus 2y right parenthesis. Here is our starting point. We'll cleverly add and subtract numbers that keep the expression the same, but allow us to complete the pattern we want. Why -8 and +6? Because -2 is the cube of -2, which is -8, and we will need +6 to complete the minus 3abc term when it equals x, b equals 1 over x, and c equals -2. Watch the pattern appear. Now we present cubes x cubed plus 1 over x cubed plus -2 cubed, and then minus 3abc becomes +6. This matches the identity. A cubed plus b cubed plus c cubed minus 3, abc equals open parenthesis, a plus b plus c close parenthesis times open parenthesis, a squared plus b squared plus c squared minus, ab minus, ac minus bc close parenthesis. Let us substitute a equals x, b equals 1 over x, and c equals -2. First factor becomes x plus 1 over x minus 2. The second factor is a squared plus b squared plus c squared, minus ab minus ac minus bc. Now simplify the second factor term by term. X times 1 over x is 1, so minus ab becomes -1. Minus ac is minus x times -2, which is plus 2x. Minus bc is minus 1 over x times -2, which is plus 2 over x. So the inside simplifies to x squared plus 1 over x squared plus 3, plus 2x plus 2 over x. Do you notice a perfect square pattern inside the parentheses? Think of a plus b plus c, all squared, which equals a squared plus b squared plus c squared plus 2, a b plus 2, a c plus 2bc. If we set it equal x, b equal 1 over x, and c equal 1, we get exactly x squared plus 1 over x squared plus 1, plus 2 plus 2x plus 2 over x, which simplifies to x squared plus 1 over x squared plus 3, squared plus 1 over x squared plus 3, plus 2x plus 2 over x. So the inner factor is the square of x plus 1 over x plus 1. Therefore, Our final factorization is open parenthesis x plus 1 over x minus 2 close parenthesis times open parenthesis x plus 1 over x plus 1 close parenthesis squared. And remember, x cannot be 0 because 1 over x is involved. Let's write the problem clearly on screen. Step 1. We want a sum of 3 cubes. Rewrite -8 as parentheses -2 parentheses cubed. Now we can view this as 3 cubed terms. A cubed, b cubed, and c cubed, where it ab equals 2 minus a, and c equals -2. Quick challenge. Can you check that a plus b plus c equals 0? Let's verify that together. Step 2. Check the sum condition. We compute a plus parentheses 2 minus a parentheses plus parentheses -2 parentheses, which simplifies to 0. So the condition holds. That means we can apply the identity. If a plus b plus c equals 0, then a cubed plus b cubed plus c cubed equals 3abc. Step 3. Apply the identity. Replace the sum of cubes with 3abc. Here, that is 3 times a times parentheses 2 minus a parentheses times parentheses -2 parentheses. Multiply the constants. 3 times -2 is -6. So we have -6 a times parentheses 2 minus a parentheses. Factor out a negative to write it more cleanly as 6 a times parentheses a -2 parentheses. That is our factored answer. Quick check. Let's verify that our factor really matches the original expression. Expand parentheses 2 minus a parentheses cubed. 8 minus 12 a plus 6 a squared minus a cubed. Now add a cubed, and then subtract 8. The a cubed terms cancel. The 8's cancel, leaving 6 a squared minus 12, which equals 6 a times parentheses a -2 parentheses, exactly our final answer. Here is the problem. Step 1. Rewrite the expression as a sum of cubes. Notice that subtracting a cube is the same as adding the cube of the negative. So we write left parenthesis 2 a minus b right parenthesis cubed plus left parenthesis b minus a right parenthesis cubed plus left parenthesis negative a right parenthesis cubed. Let x equal 2 minus b, y equal b minus a, and z equal -a. Step 2. Verify the sum condition for the identity. The key identity says, if x plus y plus z equals 0, then x cubed plus y cubed plus z cubed equals 3xyz. Now, check x plus y plus z. 2a minus b plus b minus a plus -a equals 0. Step 3. Apply the identity. Since x plus y plus z equals 0, we have x cubed plus y cubed plus z cubed equals 3xyz. Therefore, our expression equals 3 times left parenthesis 2 a minus b right parenthesis times left parenthesis b minus a right parenthesis times -a. That is the same as -3 a times left parenthesis 2 a minus b right parenthesis times left parenthesis b minus a right parenthesis. Now flip b minus a to a minus b, which introduces an extra negative sign, and the two negatives make a positive. Final factored form is 3 a times left parenthesis 2 a minus b right parenthesis times left parenthesis a minus b right parenthesis. Summary. We rewrote the expression as 3 cubed. Let us read the problem. Then we will rewrite it, check a special zero-sum condition, and apply the identity to get a clean final answer. Step 1. Rewrite the subtraction as a sum. Because we have a minus sign in front of the third cube, and the power is an odd power, we can flip the order inside and change the sign. So negative, parentheses a minus c, close parentheses, cubed equals parentheses c minus a, close parentheses cubed. That turns our whole expression into a clean sum of 3 cubes. Step 2. Let p equal a minus b, q equal b minus c, and r equals c minus a. Now watch what happens when we add them. The b cancels, the c cancels, and the a cancels, giving 0. This is our key condition. When p plus q plus r equals 0, p cubed plus q cubed plus r cubed equals 3pqr. Step 3. Apply the identity directly to our rewritten sum. P cubed plus q cubed plus r cubed becomes 3pqr, substituting back p equals a minus b, q equals b minus c, and r equals c minus a, we get the final compact answer. In this lesson, we'll factor a symmetric cubic expression using Euler's identity for cubes. The expression is, open parenthesis, a squared minus b squared, close parenthesis, all cubed, minus, open parenthesis, c squared minus b squared, close parenthesis, all cubed, plus, open parenthesis, c squared minus a squared, close parenthesis, all cubed. We'll walk step by step. Rewrite as a sum of 3 cubes, verify that the bases sum to 0, apply Euler's identity, and finally factor the differences of squares. Step 1. Rewrite the middle term to turn the subtraction into a sum. Because negative, open parenthesis, c squared minus b squared, close parenthesis, all cubed equals, open parenthesis, b squared minus c squared, close parenthesis, all cubed, we can write the whole expression as a sum of 3 cubes. This simple sign flip on the base turns the minus into a plus for the cube. Step 2. Verify that the bases add to 0. Add the bases, open parenthesis, a squared minus b squared, close parenthesis, plus, open parenthesis, b squared minus c squared, close parenthesis, plus, open parenthesis, c squared minus a squared, close parenthesis. Watch the telescoping cancellation. Positive a squared cancels negative a squared, positive b squared cancels negative b squared, and positive c squared cancels negative c squared. Therefore, the sum of the 3 bases is 0. Step 3. Apply Euler's identity for cubes. Euler's identity says, a cubed plus b cubed plus c cubed minus 3abc equals, open parenthesis, a plus b plus c, close parenthesis, times a squared plus b squared plus c squared minus ab minus bc minus ca. Let p equal a squared minus b squared, q equal b squared minus c squared, and r equals c squared minus a squared. We already know p plus q plus r equals 0. So p cubed plus q cubed plus r cubed equals 3pqr. Therefore, our expression equals 3 times, open parenthesis, a squared minus b squared, close parenthesis, times, open parenthesis, b squared minus c squared, close parenthesis, times, open parenthesis, c squared minus a squared, close parenthesis. Step 4. Factor each difference of squares. Recall the rule x squared minus y squared equals, open parenthesis, x minus y, close parenthesis, times, open parenthesis, x plus y, close parenthesis. Apply that to each factor to get a fully factored answer. Let's present the final factorization. We will factor a sum of 3 cubes using a powerful rule, sometimes called Euler's identity for cubes. Here is the expression we want to factor. Left parenthesis a minus b minus c, right parenthesis, all cubed, plus left parenthesis 2b minus a minus c, right parenthesis, all cubed, plus left parenthesis 2c minus b, right parenthesis, all cubed. Here is the rule. A cubed plus b cubed plus c cubed equals 3abc, if and only if a plus b plus c equals 0. Step 1 is to verify that the 3 linear terms add to 0. Let capital A equal a minus b minus c, capital B equal 2b minus a minus c, and capital C equal 2c minus b. We check a plus b plus c. Group coefficients by a by b and by c. For a, we have 1 minus 1 plus 0, which is 0. For b, we have negative 1 plus 2 minus 1, which is 0. For c, we have negative 1 minus 1 plus 2, which is 0. Therefore, a plus b plus c equals 0. Now, we can apply the identity. A cubed plus b cubed plus c cubed equals 3abc. Substituting a, b, and c back into our specific expression gives 3 times left parenthesis a minus b minus c, right parenthesis times left parenthesis 2, b minus a minus c, right parenthesis times left parenthesis 2, c minus b right parenthesis. The factorization is complete. In this problem, we will factor a symmetric cubic expression by spotting Euler's identity for 3 cubes. Our target expression is the sum of 3 cubes minus 3 times their product. Recall Euler's identity for 3 cubes. A cubed plus b cubed plus c cubed minus 3 abc equals the sum a plus b plus c times a squared plus b squared plus c squared minus ab minus ac minus bc. We will match our expression to this identity by substitution. Step 1. Let x equal a squared minus bc, y equal b squared minus ac, and z equal c squared minus ab. This makes the structure obvious. Our expression is x cubed plus y cubed plus z cubed minus 3xyz. Step 2. Apply Euler's identity with x, y, and z. That gives x cubed plus y cubed plus z cubed minus 3xyz equals the sum x plus y plus c times x squared plus y squared plus z squared minus xy minus xz minus yz. Step 3. Substitute back x, y, and z. The product becomes a first factor. The sum x plus y plus z times a second factor, x squared plus y squared plus z squared minus x y minus xz minus yz, all with x, y, z replaced by the original expressions in A, B, and C. Welcome! In this lesson, we will simplify a symmetric algebraic fraction using the special cube's identity when the sum is 0. Our goal is to simplify the fraction with cubes built from a square difference pattern. We'll proceed step by step. Verify the zero-sum conditions, apply the identity to the numerator and denominator, factor, and cancel. Key rule: if the sum of three terms is 0, then their cubes sum to 3 times their product. I will say it. A cubed plus b cubed plus c cubed equals 3abc, provided a plus b plus c equals 0. We'll use this twice, once in the numerator and once in the denominator. Step 1. Verify the numerator's 3 base terms sum to 0. Let capital A equal a squared minus b squared, capital B equal b squared minus c squared, and capital C equal c squared minus a squared. A plus b plus c telescopes to 0 because positive b squared cancels negative b squared, positive c squared cancels negative c squared, and positive a squared cancels negative a squared. Step 2. Apply the identity to the numerator. A cubed plus b cubed plus c cubed equals 3abc because a plus b plus c is 0. So the numerator becomes 3 times a squared minus b squared times b squared minus c squared times c squared minus a squared. Step 3. Do the same check for the denominator's base terms. Let p equal a minus b, q equal b minus c, and r equal c minus a. P plus q plus are also equals 0 by the same telescoping idea. Step 4. Apply the identity to the denominator. So the denominator becomes 3 times a minus b times b minus c times c minus a. Step 5. Form the fraction and cancel the common factor of 3. We get the product of the squared differences over the product of the simple differences. Step 6. Factor each squared difference using difference of squares. I will say the rule x squared minus y squared equals x minus y times x plus y. So the numerator becomes the product of 3 pairs. A minus b times a plus b, b minus c times b plus c, and c minus a times c plus a. Step 7. Cancel the common factors in numerator and denominator. The 3 cancels, and so do a minus b, b minus c, and c minus a. We are left with a plus b times b plus c times c plus a. That is our simplified result. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.